All right. Hello, everyone. Welcome back to Comp 2160 Programming Practices. I hope that you are all doing okay today. I posted a video about design by contract on Tuesday. I posted it on Tuesday at like 9 o'clock at night. And then I hope that you watched it yesterday in place of yesterday's class. While you were watching that video yesterday, I was out at the farm and I took a couple of pictures of animals that I'd like to show you right now. This one was called the guinea peafowl. I've never seen this before in my life. I've never seen any of these before in my life, but they are like that. The feathers on their body is really beautiful. Like it's just dots and dots everywhere, and I really liked it. Those are the legs of some small children. They're non-identifiable legs, so I think it's safe for me to show you this picture. The other photo I took is of another bird, and this was the most majestic thing I saw all day, was this turkey just strutting back and forth with its plumage just sticking out. And it was very proud. This farm is called Morning Sound Farm. It's near Sanford, Manitoba, if anyone knows where Sanford is. It's kind of like southwest of the city, southwest of Winnipeg, about 30 kilometers. And I learned, I'd never heard of this before. I learned that this place used to be a feedlot for cows, for cattle. But then in the very early 2000s, there was like this major crisis related to mad cow disease. And so a lot of the cattle farming industry kind of went down because of that. And this farm was one of those. And they basically reconstructed themselves as what I believe to be this educational farm. And like they have 8 to 10 school buses every day coming through this farm. My favorite part of this whole farm was the kitten holding station. They had it's a farm, so they've got cats everywhere. And I got to hold a bunch of kittens. And I'm a big sucker for kittens, and I loved getting to hold them. And they've got those, I don't know if you've had kittens before, but they have those extra sharp claws that just dig into you as they climb up your body. And it hurts, but you love it so much. Anyway, that's a real digression from what we're supposed to be talking about. So today we're going to be continuing to work on strings.c. This is code that I updated in the Design by Contract lecture. So please take a chance to get that latest version of the code. That's what I'm going to be working from today when we're working on this in class. And if you haven't gotten the idea already, we're going to keep working on this for quite a while. This is going to be a long-term example that we're working through and adding stuff to over time, excuse me. So by the end of today's lecture, you should be able to define the pre and post conditions for a routine. You should be able to define the invariants that encapsulate the valid states of an ADT, and you should be able to use preconditions, post conditions, and invariants to validate the runtime behavior of an ADT being used in an application. These are all of our design by contract learning outcomes. And I'm going to do like a super quick review of design by contract. I'm assuming that you've watched the video, and then we will do a little quiz, and then we will keep going with this. But we're going to keep doing this with strings and all the stuff that we're doing with strings and any other code that we're doing now. I'm going to try to make sure that I am modeling this for you. I want to make sure that I'm thinking about preconditions, postconditions, and invariants, and I want to make sure that I'm modeling it for you so you can kind of see different examples of this going on over time. I want to also continue to work on strings in terms of defining the implementation of an ADT with a private data structure. So in the very last class that we had together, we got to a point with that strings example where we have a structure, we have some functions, we did some dynamic memory allocation, and I'd really just like to keep going with that, with the long-term goal of taking the code that we've got with an array and switching it out to use a linked list without having to change the main code that we're working with, the library that we're building. But before we get to any of that, we have a term test tomorrow. This is the term test for the course that we have. And the material is going to be up to and including design by contract. So what was posted yesterday as the last material that's eligible for this term test. We're going to like do a little bit of a reviewing of design by contract today. So there's not really anything new about design by contract in today's lecture. It's more just confirming that we've got the general idea. The test is going to be 75 minutes, so it's just going to be during this time slot. We're going to be in this classroom together, and you'll have the full 75 minutes to write the test. There's going to be a couple of multiple choice questions. There's some short answer questions. There's some written and drawing longer answer questions, and then there's going to be a programming question. When you're thinking about programming, the programming question that I'm giving you is not really intended to be like a tricky, difficult to understand problem. It's something that you should be familiar with already. It's a straightforward thing to implement. This is a course on programming practices. I'm not looking for you to solve tricky problems. And you're going to be evaluated on your application of programming practices on the programming question. So these are the things like the best practices document that's in the course webpage, with the exception of that block, that comment block that goes above functions. I'm not expecting you to write all of that out on a term test. That's not something I'm looking for. Being consistent with programming standards, using defensive programming, so using conditional statements to test the inputs that are being given to you, applying design by contract, so using the stuff that we talked about in the last couple of classes. If you have a written answer that is a longer answer, so you have a box that's, you know, a reasonably big size, my expectation is that you're writing full sentences when you're asked to write full sentences. If you have options that are other than full sentences, I will make sure that that is in the question itself to say, like, you can do it this way or this way or this way. But the default should be that if you're writing a longer written answer, it should be in full sentences. The last point is that the seating for this test is going to be assigned. We are in this room, but when I print your tests, they are going to have your name printed on the test. I'm going to send you an email later today that tells you what paper number that you are going to have. We're going to be starting at this front row and kind of going backwards. I will put a map of seat numbers up on the screen when you're all coming into the room. Please bring a photo ID with you. Just put it on the table in front of you. It should have the same name that you use to identify yourself in UM-Learn. That's where I'm getting your names from. It doesn't necessarily have to be your student card, but please bring photo ID with you that shows the name that's in UM-Learn. If you are scheduled to write the test in an alternative location, then I will be delivering the paper that has your name on it in that alternative location. If you're coming here, you have to find your seat with the paper that you've got. That's what I want to say about the term test. And at this point, I want to just open the floor for questions about the test, about material, about anything and everything. Yeah.
For like the programming questions, it's going to be like something along the lines of like testing the concepts of like having a search or like having additional statements to block certain like whatever problems that you could have on the input. And then even on like the output, writing like comments or pseudocode of like what you think the output is supposed to be, or is it like that kind of stuff, or is it like actual code, or is it more pseudocode, or is it?
So the question is about the kinds of things that you might be expected to do for the programming question. I'm expecting you to write C. So it has to be like reasonably compilable C. If you're missing a semicolon, I don't really care. Like that's something that you'd be able to figure out with a compiler. If you put a brace in the wrong place, I don't care. If you forget the name of a function that you could be calling, I don't really care, as long as you describe to me in a comment what that thing is supposed to be. The thing that I'm assessing you on is programming practices. So yes, checking your inputs, using assertions, using conditional statements, trying to basically avoid getting any of the runtime exceptions that you might get with Java. Yeah. Yeah.
So on like 2140, comments are expected on our written coding and answer, because that's good practice.
So comments are expected on your written programming when it makes sense. So again, I'm not expecting you to write the block comment for a function. So you don't have to like do /*** and then like inputs and outputs. I'm not expecting that because that would take a long time for you to just write that out by hand. If there's something where you have a conditional statement, I would expect you to comment, why that conditional statement is there, what it's supposed to be preventing or what it's doing, but not like longhand, extremely verbose comments. So comment why you're doing things as opposed to what's happening, but yeah. Does that answer your question? Okay, yeah.
So, design the contract. You said it's a set of tools that we can use to ensure a good programming practice.
Yep.
Those conditions, preconditions, index. What kind of questions can we expect concerning that? I mean, not like what kind of conditions about that context.
So in terms of trying to figure out what you might be expected to do, what you might be expected to answer in terms of a question, my advice is to look at these learning outcomes, because this is what I'm doing when I'm writing a test question. On the test, what you're going to see is that I've got a question, and then beneath the question, the box where you'd write your answer, I have the learning outcome that's being assessed. So define the pre and post conditions for a routine. I would expect you to tell me what the preconditions for a block are, what a function are, what the preconditions for a block are, or what the preconditions for a function are. Use preconditions, postconditions to validate. I'm expecting you then to be able to write assert statements in a piece of C code that would actually enforce those things. Does that answer your question?
Yes.
Okay, good.
Great.
Yeah, great. Yeah.
Explain first memory allocations.
So we have not done first fit memory allocation. So here, I'm going to pop this open because I want to point at specifically the thing that you're talking about. So this is the Department of Computer Science homepage. And on this course offerings page, there's a list of course syllabuses for all of our courses. And they are all filled with these calendar descriptions, but then a lot more detailed description about what the courses actually are. And the learning outcome that you're looking at specifically is a little bit further down here. Describe the concepts of in-application memory management, such as first fit memory allocation, the runtime stack and heap, and garbage collection. First fit memory allocation. So part one of the answer to this question is we have not done this part. We have not done first fit memory allocation. We haven't done garbage collection. We know where the heap is in terms of the virtual address space for a process, but we don't know much about it in terms of what goes into it. We know a lot about the runtime stack. I'm not going to revisit this. This is everything, like this is completely covered as far as I'm concerned in the context of this course. That doesn't answer your question that you asked, but I think that it hopefully gives you a bit more context of what this is asking. First fit memory allocation is when you have a big chunk of free space, you will be given a big chunk of free space like something that is the heap. When you're allocating and then deallocating things, so think about this like files on your file system in your folders. You create new files, you delete them, you add more files, you delete them. Every file that you have has a different size. It fits onto your hard drive in some way. First fit allocation is do a linear scan of the space that you have to find the first space that's big enough to fit the thing that you're trying to allocate right now. That's the 30-second summary of what first fit is. That is not going to be on this term test. The only thing in here that we've really covered in detail is the runtime stack. So we visualized it in terms of the layout of an address space. We visualized it in terms of what happens when you call a function. So stack allocated variables are going to be put onto that runtime stack. We visualized a little bit about what happens when you do things like return addresses that are on the runtime stack and you keep calling the same function over and over. We visualized what happens when you run past the end of your stack frame on the runtime stack and you start clobbering other things. So using something like scanf to read a string, you're going to start overwriting other parts of the stack frame than what's the string that you had intended to fill. So that was a really long answer, sorry, but does that answer the question that you had? Okay. Okay. Yeah.
We talked about linked list. Are we to expect questions on linked list or programming questions and so on and so forth?
We haven't, I've used the words linked list to say that I want to do linked lists, but we haven't done linked lists in this course yet. I mean, at this point, I really hope that you can do a linked list in Java. We're going to do it in C. We will do it in C. Next week, the plan is basically on Monday, we're going to start doing linked list and testing. But for now, there's no expectation that you're going to do linked lists on this term test. No. Yeah.
Just to really clarify that, like the programming type of questions that we're going to get is pretty much not really going to be about the programming itself. It's more so about like the programming standard practices that you're utilizing. So it's not going to be like an actual like real problem to solve. It's more of like a basic programming idea that we just should kind of know how to do in C, and then it's more about how you handle it.
Yeah. So to summarize your question, and again, correct me if I'm misinterpreting what you said. It's not a tricky problem-solving problem that I'm asking you to program. No, it is not a tricky problem-solving problem that I'm asking you to implement. It's a lot more about adhering to good programming practices. So the problem involves not much more than an array, and there shouldn't be a lot of thought that goes into how to work with that array. You should just be able to figure it out. It's no more complicated than anything I've done in class, for examples.
So we can expect questions about maybe parts of memory and the pointers in the midterm.
You can expect pointers to be on the midterm in the same minimal way that we've used them in the class, yes. You can expect there to be questions about memory that are related to this learning outcome here. So again, with the whole visualizing the stack and how it changes and what kinds of things go into the stack. We okay? All right. If you have any other questions about the term test, my very strong preference is that you post that question on the course forum as opposed to emailing me your question. In terms of, I want to make sure that everyone in the class has access to the same information. I don't want to tell one person by themselves something that nobody else has access to. I want to make sure that everybody has access to it. So if you do have any questions about the term test, please ask it on the discussion forum on the course webpage. All right. So if there's no more questions about that, let's talk about design by contract. So design by contract is really just explicitly stating, so we've got a bunch of code that we have written. We're starting to build up this interface, this public interface for a data type. As we're building up this public interface for a data type, me, the programmer who's making this implementation of that public interface, I have a certain set of assumptions about what you're giving to me as input. So you are all using my library. I am making the library. I have certain assumptions about what you are giving me. Usually things like, I don't want negative numbers in this function because I'm working with arrays internally, or there's no concept of a negative index in a list that I've got. I want you to pass me things that are non-null. If you pass me something that's null, I can't really do anything with that. This is going to lead to null pointer exception in Java. This is explicitly stating those assumptions. So like literally in plain English, this is what I'm expecting as input. It should be greater than this or less than this. It should not be null. And then explicitly enforcing in your implementation using this assert function. These are going to be both inputs, what you are giving to me, and outputs, what I am giving back to you. I promise that this will not be null. If the inputs that you gave me are valid, it will be a valid thing that I give back to you. While I'm making changes to the object that you've passed to me, I guarantee that it will be in a valid state when you get it back. So when we're working with strings, I guarantee that I'm going to put a null byte in the right spot, and there will be a null byte at the length of that string. This is explicitly about inputs provided by programmers. If I didn't make that clear yesterday, I want to make it 1,000,000% clear right now. This is about getting null as an input. If you've got a keyboard in front of you right now, quickly look down at it, please, and then identify where the null key is on your keyboard. My parents cannot type null as an input. They cannot type null. They can hit enter and give me an empty string, but they cannot pass null to a function in the code that I've written. This is 100,000% about programmers passing things, programmers getting things back, and the internal state that we have in our private implementation. Are there any questions about design by contract? Can you repeat that, please? Design by contract is enforced with assert statements. And you can do this in Java and Python and C. All of them have an assert statement. Yeah.
In the video yesterday, we did an invariant with the check string function. And in that function, we didn't utilize the diff and def and debug and diff.
Yeah.
And then even when we used that function in main, we didn't use diff and def either. And I'm wondering, is that okay? Are we supposed to use it at some point?
Okay, so that's a great question. The question is about using if, ndef, and ndif, specifically ndebug. So that's not something that I made up. That's a thing. That's an agreed upon variable name for our preprocessor. Assertions can be expensive. They are for programmers. So when we build our code for ourselves and I'm running through tests, I don't want to see segmentation fault. I want to see assertion violated at line whatever. This is the assertion that was violated. When I give this to my parents, I'm assuming that I should never get into that state of seeing that assertion violated whatever. And so I can compile my code by passing this ndebug flag that says all assertions should be turned off. Assert that you get from assert.h itself is wrapped in if ndebug. If ndefine ndebug. If ndebug is not defined, then do the assertion. If it is defined, then do it. There was part of this code, so let me quickly pop over to this strings.c since we're here. And I'm going to zoom out just a little bit. So if I go way down here to char@, I use this if, ndef, ndebug, and endif preprocessor directives. Here on lines 97 through 100, I didn't actually have to do this because these two assertions themselves are going to be turned off when ndebug is defined. Up there on lines 79 through 83, those lines are not assert. So they're going to get run when this code is run. And for me to run an strn copy when I'm just trying to access an element in an array is kind of bananas. It's kind of crazy and it's quite expensive because it's going to take a bunch of memory and then a linear copy algorithm just before we actually start doing that stuff. So I'm not sure if this answers your question. I think it does, but I'm going to confirm with you. We're not doing it with assert itself because assert just has that built into it. We are doing it with other things because they don't have it built in.
In the check string function, assert right away because I have to like figure it out
Yeah.
beforehand.
Yeah.
Would I surround that with the event def
Yes.
in that function?
Yes. Yeah, in this function itself. So this is a good place here. Exercise for the reader. Check that the number of characters before the null byte is equal to length. If you write a loop to do that in check string, it would be a good place to wrap. You could put an assert inside the loop, but you should also just wrap the whole thing with if end f debug, and debug, and then end if. Just that part of it. Yeah. Yeah.
So when does the different when does it get run like one time? Is it
That's a good question. So this is something that happens at compile time. So we did look at this preprocessor state with the -e flag to Clang. So if I do -e strings.c, I'm going to pipe this into a pager called less so that I can see it. And if we go down to check string here, we can see that assert has turned into this kind of gnarly looking the assertion here is happening on this line. It looks kind of crazy. Assert turns into that. We don't have preprocessor directives in that because the preprocessor has gone through and changed assert into that. Assert itself is actually a preprocessor directive. It just doesn't look like it because it's all lowercase. So it's not actually a function, it's a preprocessor directive. If I do clang -e, and then I say -d_n_debug. So this says set a flag on the preprocessor. If I do this and I go to check string, all of those crazy long statements that were assert are now just nothing. So casting 0 to void is like a non-operation. It doesn't actually do anything. When this gets to the code generator, these will just get optimized away. And then the whole check string function will just get optimized away because it doesn't actually result in any changes. If I go down to, so let me run this one more time. And I'm going to go down to char at. So char at here, one more time. Here we've got that block that's doing the copy of string, and then it's doing the strn copy. In the original code, it had that ndebug statement. So if I do this again with ndebug and I go to char at one more time, all that stuff has been taken out. So it's conditionally being compiled in or out based on what that flag is that I'm setting. When I give this to my parents, when I write this code and then I compile it, I'm going to give it to them with this flag because I don't want those assertions to run. When I'm working with you, when I'm doing this by myself, I'm not going to do this flag because I want those assertions to be turned on to give me more informative error messages than just segmentation faults. Yeah. Any other questions? That's part of the text replacement engine, yeah. That's part of the preprocessor. Yeah. Yeah, yeah. When ndebug is not defined. So this -d here, this is the same as saying number define in our preprocessor. Ndebug is just the name of the variable, and then that if ndef is asking if it's not defined, then do something. If you compile it without ndebug, then assertions are on. Yeah. Yeah. And when you do it with ndebug, then they're off. Yes. Which is opposite of Java. Java doesn't have assertions enabled by default. So when you were writing your solution for assignment 1 and you were looking at the code in Java, it had some asserts. those asserts are turned off by default. You have to specifically turn them on as a runtime option when you run the Java command, which makes sense because Java is filled with exceptions that help us figure out what the problem is. We don't really need assertions quite as much. Here, we're trying to prevent those exceptions from happening by using the assertions to help us do that. Yeah. Yeah. So the question is, since these assertions can be turned on and off, do we have to actually enforce these things with our conditional statements? So yes, where it makes sense. I'm going to go back to here, and I'm going to go back to here. In this space here, where we've got characters does not equal null, where we've got numchars is greater than 0, because those assertions can be turned off when I compile my code, I should be putting conditional statements in here to also check that. So before I even start doing any of this other stuff, I should wrap this entire block with if this is not null and if this is greater than or equal to 0. Yes. Yeah. Some of them don't really make a lot of sense necessarily to have conditional statements for. Like some of the invariant stuff gets to be quite involved. You don't want to turn off having this loop that goes through every character to find the null byte just to re-implement it anyway in all the places that you've got. It doesn't really make a lot of sense. But some of these basic preconditions you can still have conditional statements for.
Is there any other thing that we can do with malloc?
Is there anything else you can do with malloc?
It just assigns the memory, right? Memory location in the heap.
In the heap, yeah. We'll talk more about malloc. We will talk more about malloc. But for now, it assigns some memory to you that's been allocated in the heap, and you can use it. Yeah.
So this is like, is it in a stack, in a heap in the stack?
The heap is not in the stack. They're two physically separate locations in our address space. But as we run our code, the stack is changing underneath us all the time. The heap is this entirely separate thing. So when we do an allocation in the heap and we return from a function, that allocation in the heap is still allocated. And then so we can that's why we can pass that around to other functions safely. Yeah. The answer to that is it depends. So the question is, if I've got a string literal, where is that string literal? So I'm going to go to main.c here, quit this. So here I've got a string literal Franklin. That string literal is in the code section. It's read-only because it's part of the program that you've written. It's part of the source code, sort of. If I were to do something like, say, char my name, square brackets like this, and then initialize it with f, r, and so on, that's going to be allocated on the stack for the main function. This is a really pedantic thing that's not super important. Yeah. I hope that answers your question, and I hope it gives you a little more context about the question. So again, this is something that we'll talk a little more about. I'm going to open strings.h here. When we've got this array here, it's actually just turning into this underneath us. It's turning into a pointer underneath us. In terms of arguments to functions, they are the same thing. They are actually the same thing because you're passing the value of an address in both cases. We've just been using those square brackets up to the point where we know about pointers to kind of not have to talk about pointers. But now that we know about pointers, I'm probably going to stop using those square brackets and just start writing the pointer symbol. Yeah. Yeah. Any other questions? Okay. Okay. Okay.
We initialize with 0.
Yes.
Why can we initialize with 0, but we can also replace the zeros with different like characters, but we can't initialize with characters and replace those characters with like different characters.
We can. If I'm understanding your question correctly, we can.
I'm saying, so for example, chart line, when we initialize with right,
Yeah. Yeah.
when we're doing something to it in memory, it overwrites. Does it actually overwrite or it gives us an
So this array right here, this is an array that's been stack allocated. So if I make changes to this below this, if I say my name at 0 is equal to the null byte, that's making changes to that array, that stack allocated array. It's making changes in stack. Yeah, it's going to overwrite it. This string literal is not named anything. There's no variable name that I have to refer to this, so it doesn't make sense for me to be able to make changes to it. Okay. Are there any questions about design by contract specifically? Yeah.
input, output.
Yes.
So would the external state input or output?
External state, so if we're thinking about our interface here, this is kind of like where our responsibility ends in terms of design by contract. Everything that's behind this part, the implementation, so strings.c in this case, this needs to do design by contract enforcement. But once you're running in your code that's using my code, I have no control over what you're doing. The way that I can control that you are not going to make changes to the internal state of my objects is by doing this on line 9. I'm telling you that there's a type available, but I'm not telling you what it looks like. You can do memory manipulation on that if you want. I mean, you can go into an address and just change a value if you want. I can't stop you from doing that, but I can make it really hard for you to know what you're doing with my object. And that's how I prevent external state changes from happening, is just to make it as hard as possible. Okay. Sure. That's okay. Interfaces is kind of related to design by contract in that we're making statements in our interface about the contract, and we're implementing the contract in the implementation of our interface. But you can do an interface without having design by contract. I can build an interface and not care what you pass me and just segmentation fault every time. Yeah, yeah. Okay, let's do a quiz. So I'm going to be asking you some questions in this quiz that have to do with some code. And I want to have the code on the screen instead of in the question. So I'll put that back up in just a second. This is the code that we're talking about in the questions that I'm asking you. So whenever you see a question that's being asked in this Mentimeter, it's referring to that specific code segment right there. All right. Okay. Which of the following are preconditions for this function prototype? Lots of people are picking this. This is definitely correct. So there's like some context that we all just know about in terms of how strings work and what substring means. The start of a substring can't be less than 0. If I ask for the start of a substring to be less than 0 in Java, I'm going to get an array index out of bounds exception. In C, it's just going to work, but I don't want it to work. I want to make sure that we are stuck in the bounds that we've got. So a precondition for this function prototype is absolutely that start must be greater than or equal to 0. End must also be greater than or equal to 0. I can't really go from start to -7. Again, it just doesn't really make a lot of sense. In Python, you can kind of do this in Python because a string just is a list, and with lists you can do like reversing of a list using slices. So you can do like start at position 1, colon, go to -7, and then it will reverse and give you the substring at the same time. But that's a Python idiom. In C, I don't want to do that. I just want to give you a straight up substring. So n must be greater than or equal to 0 is absolutely a precondition for this prototype. S must not be null. So we are now working with pointers here. And when we're working with pointers, it's possible for me to pass null to your function. It was possible before with arrays, even though I had those square brackets, because they are the same thing, it was possible for me to pass null. But now I explicitly want to say, you should not pass null to me. This one here, start must not be null. I'm going to give the 3 people that answered this technically correct yes, technically correct. In C, null is 0, so technically you could be correct here. But semantically and conceptually in terms of C, start is a primitive type that cannot be null. So it can't have the value null itself. It could because it can be 0, but it's not going to have that value. This one here, S must not contain an empty string. This is an interesting case to me, and this is a reasonable thing to think that you don't want to give an empty string. But it's totally valid for me to ask for a substring of a string that's 0 characters long, starting at 0 with 0 length. I should just get the empty string back because it's the substring that starts at 0 and ends at 0 of a string that's 0 characters long. This is a weird case. When we talk about testing next week, this is an edge case. I want to ask for a valid thing from something that looks real weird, but it's valid and it should work. These preconditions are not comprehensive. Yeah. These preconditions are not comprehensive. These preconditions are not comprehensive, and I'm going to ask you that question, and I will allow you to answer that when we get to that point. But that is a very good point. Thank you. Okay. Okay, good, good. So post conditions. As output, I'm going to provide you with something. One thing that's a reasonable post condition here is that as a substring, I am returning to you a new instance of this string type. I'm not going to change what you've given to me. I will make that promise. I'm not going to change what you've given to me. I'm not going to reduce the size of the string that you're passing into me. Start and end are not modified. It is a reasonable post condition, but it's something that's enforced by the language just in terms of the way that pass by value works. If I make changes to start and end inside of my function, in your calling code, those values haven't changed. So there's not really a contract there for me to enforce. The returned string is valid or is null. This is 100% a reasonable thing to say as a post condition. I will either give you back something that is a valid string, Or if you violated one of these assumptions that we had for preconditions, I'm just going to send back null. And I will write that in my function comment. You will get null back if you've given me something that is invalid. The returned string is always null. That would be an interesting program to write, but that's not a postcondition for us. The returned string contains part or all of the original string. That is also a reasonable postcondition to have. Given the input and the start and the end, after we do a copy into a new object, we could go through the process of verifying that this string's contents actually equal the substring that was supposed to be given back to the caller. These postconditions are not comprehensive. These are some of the postconditions that you might have for this, but it's not a comprehensive set of postconditions. Dr. Centipede. Winner is very confident. Winner is very confident to choose that name for themselves. Shiny Pikachu has shown up. I'm delighted to see that. What are more preconditions for this function? It's okay if you restate what I've got. This is not a quiz question. This is just give me something. What are more preconditions for this function? So looking at these three inputs, what are more preconditions that you could include as part of your code? So start is less than or equal to end. Start isn't greater than the end. Yes. So these two, so three now, these are all definitely valid. Valid, yes. S should not be null. Yes. S is not null. Good. Greater than, yes. And should not be more than max of the possible length. Okay, so this one is really good. I like this one. This one is really good in the context of we are working with an array-based implementation of our string right now. We have a max possible length of our array because we are working with arrays. When we switch to working with linked lists, we're not going to have that same limitation. The limitation is going to be main memory size. There is a limit, but it's not going to be like 100 characters. So lots and lots of end is after start. So that's really awesome. Make sure that S was not modified. Yep. The string is not null or is a valid string. So yes, that is a good precondition. What does it say? Having a null terminator. I hope that's autocorrect in action. Having a build terminator. I want to call it build terminator forever now. Having a null terminator. So this one is good. This one is now kind of like, I want to take my invariant and I want to use that as a precondition. The input that you are giving to me, string S, that is my private data type, but I want to make sure that you haven't messed with it. And that's related to your question. You might be able to, I'm sorry, I'm pointing at you, but you might be able to mess with my stuff in your code. But if you give it back to me, I want to make sure that you haven't messed with it. Or I want to make sure that you haven't messed with it in a way that's going to cause it to be invalid. So this is definitely a precondition. The string is not null, or it is a valid string that has a null terminator. It's bigger than 9999. Okay, thank you for that callback. And then lots of n does not exceed the string length. Correct variable types are added. A check mark. Okay, good. This, I think, is a pretty comprehensive set of preconditions for this function. Thank you all for that. Related, what are more postconditions for this function? String is not modified. The string at end is equal to the null byte. Yes. Substrings ends with a null byte. These two, I'm going to say, are, if they are not intentionally saying the same thing, I think that they are both actually saying the same thing. S is a null terminated string. Domain expansion, I don't actually know what that means. What does it mean? Oh, is it a 2080 thing? Should Should I be embarrassed that I don't know what this is? Okay, okay, good. What is it from? What show?
JJK.
JJK.
Yes, it's a very interesting characteristic of a character.
Okay. Am I going to be embarrassed looking this up on my phone? Surprised because I'm embarrassed, or it's a JJK? It doesn't show up on IMDb.
It's a shorter name for it.
Is it anime?
Yeah.
Oh, okay, okay. Jujutsu Kaisen. Okay, yeah, okay. I will look at that later. I will look at that later. The output is a new copy of the input string. So I like this one. One way that we could kind of check this is that we could go to the extent of saying, like, I'm going to make an assertion that the address of the array that's in the string I'm returning is different than the address of the array that I have been passed. However, it would be perfectly reasonable for us to return an address inside of the thing that was passed to us as a substring. It would be totally reasonable for us to do that. The substring is a portion of what it's supposed to be. The strlen is the end minus the beginning. I really like this one. This is basically checking to see that the string that we've got based on some arithmetic here is going to be the right size. It's going to be the right number of characters that are inside of it. The substring length is less than s.length. That's good. Okay. All right, cool. Don't get segmentation fault. This is something that surprisingly we can actually sort of check. Sort of, but I will let you get to operating systems to find out about that. And that will just be a tease for operating systems. We've returned the proper length for the new substring, so end minus start. Okay, so these are really excellent post conditions. And I think that, you know, barring anime references, these are pretty comprehensive in terms of the post conditions that you might want to have for this. Yeah, please ask your question. I have to answer that by saying, please wait for operating systems. Yeah, that's the way I have to answer that. Because if I don't, I'm going to spend the next 3 classes talking about operating systems concepts. Yeah, yeah. If you're asked, so that's a good question. If you're asked a question about post conditions on a term test, how many are you supposed to give? I will tell you how many to give. If you give more than what I tell you to give, though, I'm not going to mark all of them. I'm just going to look at the first n that you give. So don't try to give a bunch hoping that, you know, n of them are correct. Is just the first n that I look at. Okay? Okay. All right. This one is a quiz question now. This is the last question. Good. Runtime errors caused by a programming error. Design by contract is very much about programming errors. It's very much about errors that can be introduced by me or you. User input, this is a reasonable thing to write here. It's reasonable to write this. But again, I invite you to find the null key on your keyboard. That's not something that a user can press as a button to give an input to my code. They can press enter and give me an empty string, but they cannot pass null to any of the code that I have written. Syntax errors, linker errors, these are going to be things that are happening at compile time, so not really so much design by contract. Specifically prevent segmentation faults. yeah, that's going to help a lot with seg faults, but that's not specifically what it's trying to do. It's trying to stop us in other places as well. So let's see if winner stays at the top. Whoa. Wumbler Jombler Gobbler. Okay. Congratulations. Both at the top and the fastest. I'm going to try and export the preconditions and postconditions that we collectively came up with and put them on the course webpage so you have access to them. I'm maybe not going to put domain expansion because I don't 100% know what that means, but I'll try to make sure that I can get that up on the course webpage. All right, cool. So thank you very much for playing along with that. What I'd like to do now is keep building our string data type. So we've got about 20 minutes left in class, and I'd like to continue to work on this string data type. So as of last class that we were together, what we've got here is a public interface. So we've declared this type as being available to use. We've defined a constructor function here, makeString, that we are able to call to get an instance of this string type. We've got a char@at function. So now we're starting to try and replicate some of the behavior that's in the string type in Java. In terms of its implementation now, so I'm going to quit my main here, and I'm going to edit strings.c. In terms of our implementation, we've now got a structure instance that gives us the properties of what this string is, but its implementation here is hidden from the caller. The code that's calling makeString does not know what the string actually looks like on the inside. It doesn't know anything about what's going on there. We started to do some design by contract here. So I'm going to add this comment here. If you do this, you should wrap this here with if ndef ndebug. If you do this, you should do that with ndebug. We have an invariant on our string type. The invariant on our string type is for a string to be valid in terms of the code that I've got, s should not be equal to null. The string itself should not be null. I'm testing this here because if this is null, I don't want to start checking properties of that thing because I'm going to get a segmentation fault, a null pointer exception. I want to check to see that the length is greater than 0 and it's less than the max string length. And I want to make sure that the characters that I've got here, the last character is the null byte in the string. That's what defines a valid string for me. Our makeString function now enforces some of the preconditions that we've got. So again, I'm making sure that characters does not equal null. I'm going to make this this interface consistent with my header file by changing this to a pointer. But again, this was happening internally, and we shouldn't even be getting compile time errors if we have square braces here and a pointer in our interface. I want to make sure that I have got an actual address that I can start working with. I want to make sure that numchars is greater than or equal to 0. I want to make sure that the number of characters that I've got in that I want to make sure that the thing that's been passed to me itself is a valid C string. And one of the other preconditions that we had in the question that I asked you was that I want to make sure that numchars is less than max string length. So I want to make sure that I'm not actually getting something that's going to be too big than I can fit into the string that I've got. I'm going to keep going down here. On line 51 here, we're now at the point of doing dynamic memory allocation. So we were able to return stack allocated structures. That was possible. And that also, as a side effect, gave us this workaround of not being able to return arrays from a function. But if I want to hide the implementation details of my structure, I have to switch to using pointers and dynamic memory allocation. If I don't want you to know how many bytes are in the structure, you can't use it on the stack because the stack needs to know how many bytes to allocate for that object. So I need to make sure that I'm using I have to switch to using dynamic memory allocation here for that. Dynamic memory allocation can return null. It's possible for me to get null back from this if there's no memory left. So if the heap space has been exhausted, it's possible for me to get null. So I have to check before I proceed. I'm going to keep going down here now to char_at. And char_at kind of ballooned into this mega function that's really just doing array lookup. It ballooned into this mega function that's just doing array lookup. We have some preconditions that we will want to use. We have some post conditions that we will want to use. And the core functionality there is on lines 87 through 90, where we've got the actual array lookup that's wrapped in a conditional statement. Okay, so that's the state that we're in now. I want to keep building on this, and I want to keep building on it kind of step by step. Here's what I want to do today to this implementation. The first thing is to add header guards to our interface. We started defining this .h file. We started writing out this .h file. But we're going to run into problems if we try to include this multiple times in multiple places. This isn't something that you usually do on purpose. It's more like if you have different implementations of libraries and you include something in one place and another place, and then you get it from both of those places. So I want to add header guards to interface. We've started to do dynamic memory allocation by getting some memory that's on the heap. With stack variables, we didn't have to care about what happened to memory because when the function was over, that memory was reclaimed by the operating system. Usually nothing happened to it, and we were able to see things like if I call this multiple times with the same values, there's no side effects. But the heap does not get reallocated when a function ends. When we go out of scope with a pointer, that heap space stays allocated to our process or to our code. We need to manage our own resources. In Java, we've got garbage collection. When a variable goes out of scope and it's not being used by anybody anymore, the JVM just cleans it up for us and we don't think about it. You do have to think a little bit about closing files when you're finished with them, but you don't even really have to think about that. In C, when we allocate memory on the heap, we have to release memory when we're finished with it. And we have to tell ourselves how to release that. I want to add some more behavior to this. So char_at is kind of lame. It's kind of a lame implementation. It's very simple, but it's kind of lame. So I want to add a little bit more behavior to this. And as we're going through this, I want to make sure that we're adding and enforcing design by contract and defensive programming. The last thing that I want to do here is explore a new keyword, which is const. Our char_at function has ballooned into this mega function because we're checking that the contents of the string are actually equal after we've done char_at. But there's a better way. There is a better way. There's a better way. So let's do it the better way instead of doing all that extra work. I wrote here probably next week when I made these slides because I was feeling optimistic, but definitely next week we will be looking at replacing our implementation with a linked list. All right, so let's get started. Header guards are preprocessor directives that prevent repeated function prototypes and type declarations. Header guards look a little bit like this, and they look a little bit like that ndebug thing that we started working with. Remember that, I'm going to switch to my code now. Remember that when I've got this interface here, so this is my .h file. In my code, I am doing include strings.h on line 7. When our preprocessor runs, our preprocessor has taken line 7 and it's replacing it with all this stuff. everything that we've got inside of strings.h. Just the entire file gets copied and pasted into that one line. There's nothing that stops me from doing this, because my preprocessor is not a compiler. It's just a text replacement engine. I'm not likely to do this, but what's more likely is if I've got a linked list.h and strings.h, and I'm using them both kind of with each other. The linked list implementation uses strings for some reason, and the string implementation uses a linked list for some reason. If we've got this relationship between two different data structures, we've got this kind of circular dependency of includes. And our compiler, our preprocessor, is going to get into the state of you have a circular include, and you just can't keep doing this. You're stuck in this cycle in your graph. A header guard is something that we use to make sure that if this unintentionally happens, there will only be one copy of this. There might be a cycle, but because of the header guard, it will prevent the cycle and break the cycle from happening. It will break the cycle, and it will also prevent things like you've declared this struct twice. Header guards are straightforward to use. If you are using C in general, we use the preprocessor directives if ndef. If ndef here says if not defined. A de facto standard, de facto means like it's not an actual standard that somebody wrote. This is just something that everybody collectively agrees upon. It's not written down anywhere that this is the way that it has to be. We've all just agreed that this is how we're going to do it. The de facto standard is to do 2 underscores and then all uppercase the thing that you are defining. So if ndef and then underscore underscore strings underscore h. If that's not defined, then I want to define it. I want to say if number defined, whoops, if ndef. I knew there was something wrong when that did not change color, but I just trucked on anyway. And yeah, anyway. So if not defined strings.h, if it's not defined, then define it. Defining it here is just going to say that there's a variable in my preprocessor that's called strings underscore h. It doesn't have a value. I'm never going to use it as a value. It's just a variable that's there, floating around in my preprocessor. I want to wrap this entire file in this preprocessor directive. So I'm going to hit Shift-G to go to the bottom. And at the very bottom of my code, this is the last line, I need to end my conditional statement. So I need to have an end if. This looks very much like if ndef and debug with that stopping parts of this from happening if we're turning off debugging. So I'll go up to the top again. If it's not defined, define it. If it is defined, then the preprocessor will just not include all this stuff again. So if I put include strings h here, and I'm going to quit this, and I'm going to use my preprocessor again. I'm going to pipe it out to less. Clang is printing just standard out. Less is reading standard in. They're connected to each other. If I go to type def struct string, I've included this twice, and we can see these lines here that say strings h. Strings h is going to be omitted the second time, so this is the only instance of that struct string. If I very quickly comment these out, and I run this one more time, if I search for struct string, it's twice. We've got it twice. So if ndef, the name of the header file, define it. Yes. That's a good question. So another option is to use pragma once. This is an alternative to if ndef plus number define. Pragma once is it was at some point a GCC specific thing. Pragmas are usually compiler specific. but then different compilers are like, hey, that's a great idea. I'm going to pick it up and do it. But it's not defined in the C standard anywhere. So Clang does this correctly. GCC does this correctly. If you're working on embedded systems where there's like a very specific compiler, it might not do that. But because if, ndef, and number define are part of the C language standard, those embedded systems compilers will generally honor the C language specification. And so you can trust that that's going to work. But yes, to answer your question, Pragma once is a valid way to do it. Yeah. Any other questions? This is straightforward, I hope. This is pretty straightforward. Good. OK, so that's it. That's header guards. The next thing that I want to do is resource management. So for every malloc, there must be a free. Now that we've unleashed this idea of using dynamic memory allocation with malloc, we become responsible for managing memory in our own application. Whenever you do malloc, you have to call free on the corresponding pointer that you've been given back from malloc. We are using malloc in our constructor function, so we have to add a destructor function. Again, you have no idea how my string is implemented, so you can't destroy it. You don't know what I've done inside of this thing. It's my job to destroy it. So I need to write a function that gives you the ability to give that to me to say that you are finished with it. So let's pop over to our code again. I'm going to add a new function in my public interface. I'm going to go down to the bottom here. I'm actually going to put this right beneath make string. So I'm going to expand this, and I'm going to say here that I want to, I'm going to have this be void. This isn't going to return anything. We're just destroying something that's been given to us. I'm going to call this destroy string, and it's going to take as input an instance of string, so string s, the thing that you want to destroy. Destroy an instance of a string. The arguments to this is s. This is the string to destroy. It must not be null, must be a valid string. It doesn't return anything, so I don't need to put anything there. I'll leave this up on the side, but I would like to start implementing this. So I'm going to zoom out. I'm going to open strings.c here on the other side. I'm going to start writing underneath make string here. We could put it anywhere, but I'm going to write it underneath this. Void destroy string. I'm going to write cstrings.h for usage. This would be a reasonable thing for you to do in your own library code that you're writing. Put the comment in the header file and then just say in the implementation, refer to the header file for the documentation rather than copy pasting or whatever. It's a reasonable thing to ask. So I'm going to destroy a string. The thing that's being passed to me is an instance of this. It should not be null, so I'm going to immediately do a precondition assert here. S does not equal null. I'm going to call my invariant. This must be a valid string, so I'm going to call my invariant. My invariant, remember, is called checkString. I'm going to pass to this s. CheckString itself also checks to see if that thing is null. That's OK, because it's going to get compiled away when I do this without debug turned on. Once I've got a valid string, then I need to release my string from being allocated. The way that we release something from being allocated is to pass that string to the free function. This releases those resources that we've acquired in the heap, and it basically says that when we call malloc again, some other point, we can just reuse that space on the heap. If we never call free, we are leaking memory. So if I never call free, which I'm going to do right now, I'm not going to call free. I'm going to change into this directory here. So this is lecture 11. I'm going to open main.c. Right now, I've got this my string is equal to make string. I'm going to do this while true I'm going to change into this directory in another terminal here. I'm going to make everything again. So I need to recompile my library. So clang wall strings.c, the -c flag here for just compile it. I don't want to link it. This is not runnable code yet. -o strings.o. That's good. I want to compile main now. So main is this separate file. We don't have them in the same file anymore. So I'm going to say clang wall main.c strings.o -o main. We get a warning. It's set but not used. That's totally fine. I'm going to run main, and I'm also going to close this for just a second, and I'm going to run a program called top. Top is a program that will print out what processes are currently running on my system and how much memory they've got and how much CPU time they're using. Right now, I'm calling makeString over and over and over again, 8 bytes at a time, and I'm never releasing this memory. And if I zoom